All right, so this is going to be about exponential functions. So these are going to be the most basic exponential functions of the form f of x equals a to the x. So you might actually see some that get a little bit more complicated later. So these are like y equals a to the x, or it can be any letter that you want. It could be b to the x, all right? And then you might see some that have another multiplying factor out in front later. So we'll talk about a couple of those in a little while. But let's just start with the basic ones where the form is just a base to the x power. All right, so let's start by talking about these exponential functions. Now, the one thing that you should remember is that this base, and I personally prefer the letter B for base rather than A. So if you want to use B so that you remember it's the base, that's fine with me also. But that base has to be greater than 0 and it cannot equal 1. And this basic exponential function has a domain of all real numbers. So the domain, this symbol means all real numbers, or negative infinity to infinity is the domain, meaning that any real number could be the exponent, but then the range is 0 to infinity, and the line y equals 0, or the x-axis, is a horizontal asymptote, and the graph has one of the following shapes. So here are the different shapes that the graph could have. So this particular one here, if you look at it, is this one increasing or decreasing? Well, I see that it is going upward like this, so it's increasing. And the domain is all real numbers, negative infinity to infinity. And then the range is going to be 0 to infinity. The asymptote is just one horizontal asymptote at y equals 0, and it has a y-intercept of 0, 1, but no x-intercept. So it has a horizontal asymptote, but no vertical asymptote. All right, so no vertical asymptote, and then also it has no x-intercepts. All right, now the thing is that you have to make sure that this is actually, again, I'm going to just make these all b's. All right, so this is y is b to the x when b is greater than 1. Now if b is actually less than 1, but still positive, so between 0 and 1, then you can see that something else happens, and this is actually decreasing. All right, so then the domain is still negative infinity to infinity. The range is still 0 to infinity. It still has a horizontal asymptote at y equals 0, and it still has a y-intercept at 0, 1. So the main difference here then is that for this one, y equals b to the x, that base b is a number that is a fraction between 0 and 1. So hopefully that makes sense of what is going on here. So the other thing that might be of maybe some use to you to sort of point out on the graph, and I'll point this out here, is that another point that happens to be a common point that people will pick is, here, say 1, and this will actually be the point 1 comma b. All right, so if you look here, here's the point 1, and this is the point 1 comma b. So if you look here, again, this b is a number that is less than 1, and this b would be a number that's bigger than 1. So there you go. So now let's look at this in the next page. And again, if you have any questions, you can always feel free to ask at any time. But here is an example here. So let's see. So find the exponential function, and I don't know why that's so small, but just y equal b to the x, whose graph is given. All right, so we have 2 points here that are easy to find on our graph. Of course, -1, 1/5, and 0, 1. So what you can do here then is just substitute these the points into the equation to figure out what the base should be. So y is equal to b to the x. So I'm going to substitute the -1, 1/5 to find out what b is. So this is x and that's y. So we have 1/5 is equal to b to the -1. And then b to the -1 means 1 over b. So 1 over 5 equals 1 over b. And then I can just equate the denominators since the numerators are the same, or I can just cross multiply 1 times b is b, 5 times 1 is 5, and I see b is 5. So that means the graph is f of x equals b to the x, or f of x equals 5 to the x, because b was 5. All right, so if you don't have any questions, that's okay. But again, feel free to ask. But I'll go ahead and do another one here to give you a minute to ask if you would like to type it in or whatever if you do end up having questions. So it's the same thing for this one. If we want to find the equation, we're having a point that's given to us. So y is equal to b to the x. And then if we want to find b, we're going to substitute the -3, 8 to find out what the b is. So this will be, what will it be? Oh, yeah, so 8 is equal to b to the -3, but b to the -3 is the same as 1 over b to the third. So then all I need to do then is actually go ahead and, uh, well, cross multiply. If this is 8 over 1, that's 8b cubed is equal to 1. Divide by 8 to get b to the third is 1/8, and then take the cube root. So if I take the cube root on each side, I get the cube root of 1 over 8. And so b is equal to 1/2. So that's the cube root of 1 over 8. So then that means f of x is equal to b to the x is then f of x equals 1/2 to the x. Now, one thing that I should know is that this graph was increasing, so I knew that the b needed to be greater than 0, and it was actually 1, and it was 5. All right, and this graph was decreasing, so I knew that the b had to be between 0 and 1, and it was 1/2. All right, so that's actually how I would have some idea of whether or not I was actually going about doing one of these problems correctly or not. So hopefully that makes sense. And before we go to the next one, I actually am going to look up another example that is not in here to make sure that you you get the you get everything here, because I do want to say one more thing about these types of problems. Okay, so let's see. So I am going to do another example here, and this one would be one that, and Susan, you asked about one like this yesterday, but I'm going to do it again because I want you to see how I know that it's a different problem than the ones that we just did. So the graph of an exponential function passes through the points 2, -12, and 3, -24. So we want to find the exponential function that describes the graph. All right, so just find the exponential function that describes the the graph. All right. So here's what this one actually looks like. So we have at 2, -12. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So 2, -12. And at 3, -24. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So that's -12, -24. So 3, -24. And then I see here that I I actually don't have any idea of this graph will um, what this graph will look like, except that the points seem to be decreasing in nature. So I think that I'm pretty sure it looks like this. So yeah, so I'm pretty sure it looks like that, which is it's definitely exponential, but I'm not sure that you would know that unless they told you that you want it to find an exponential curve. So how do I know that this problem is still an exponential function, but it's different from ones like these? Well, if you look at all these so far, there was a point at 0, 1. All right, and this had a point at 0, 1. Even though our definition had a point at 0, 1 and a point at 0, 1. So if there isn't a point at 0, 1, then you might want to try something else to try to find the equation of the graph. All right, so that means that this would be of the form then the y equals ab to the x, and y equals ab to the x, and then I'll substitute the points. So 2, -12, and 3, -24 were the 2 points. So for this point, I have -12 is equal to a b to the second power, and here I have -24 is equal to a b to the third power. And then what I can do is actually just divide this by b squared. So -12 over b squared is equal to a. And then I'll substitute that in for a. So -24 is -12 over b squared times b to the third. Then b to the third over b squared is b. So -24 is -12b. Then I'll divide by -12 on each side to get that 2 is equal to b. And then since 2 was equal to b, I'll substitute that back in here to find a. So negative 12 over 2 squared is a. So negative 12 over 2 squared is negative 12 over 4, which is a. And negative 12 over 4 is negative 3. So negative 3 is a. So I know that this is of the form y is a b to the x, or y is negative 3 times, and b was 2, so negative 3 times 2 to the x. All right, so that's how I would do this one. And again, I knew that this one was going to be a little bit different because there wasn't a point at the 0, 1. All right, so I hope that you enjoyed that and that it gave you a sense of like why you would do one procedure one time and maybe something different a different time. But the main thing I was looking for was that point at 0, 1. All right, so now, yeah, that's quite a lot in my opinion, but partially because the numbers are so large, like negative 24. But you see that just a negative 3 and a 2 end up giving very large numbers. So that's why this is called exponential growth or exponential functions, because the numbers get really large really quickly, whether that's in the negative or the positive direction. All right, so let's look at the next page, and that would just be to sketch the graph of each exponential function and then determine the domain, the range, and the asymptote. So remember, the first thing was to notice that if you have y equal b to the x and b was greater than 1, then the graph would actually be increasing, all right? And then if y is equal to b to the x, but b is between 0 and 1, then the graph is decreasing. So I look here at f of x equals 1/5 to the x, and I see right away that this has a base of 1/5, and so this graph should be decreasing. So I know that there is a point at, there's always a point at 0, 1, because f of 0 is 1/5 to the 0, which is 1. And then there's a point at 1b, but b was 1/5, so 1/5, and that's again because f of 1 is 1/5 to the first power, which is 1/5. All right, so those are just easy points to find. And so then I'll go ahead and graph this. So there's a point at 0, 1, and then at 1/5, and I know this is decreasing, so it looks like this. And that's it. All right, so here was the 0, 1, here is the 1/5, and then all I need to do is write down the domain and the range in the asymptote. So if I look here, I see that there wasn't any shifting up and down, so the asymptote is still at y equals 0. And that means that the domain and range will also stay the same. So the domain is all real numbers, negative infinity to infinity. The range is still 0 to infinity. And the asymptote is still y equals 0. So hopefully you enjoyed that. And now let's try another one. So this is similar, but this one has a base that is going to be greater than 1. So here b is equal to 5, so this should be an increasing graph, and there's a point at 0, 1, and there is a point at 1b, which is 1, 5. All right, so now all I need to do is use that to sketch the graph. So there's a point at 0, 1, and at 1, 5. So here is, and it's increasing. So it looks like this. So here's 0, 1, here is 1, 5. The graph was increasing. And then I can write down what the domain and the range and the asymptote is for this graph. So there wasn't any shifting up or down. So the domain is negative infinity to infinity. The range is still 0 to infinity, and the asymptote is still y equals 0. So again, if you have any questions, feel free to ask, but we're going to switch over to a few problems where the graph is shifted to the different directions here. So I actually have to find that page here. So, all right. So here we go. We have f of x is equal to 4 to the x minus 2 minus 2. So what I see here is that I have the minus 2 in the exponent. So that would mean a shift 2 units to the right, and the minus 2 after means the shift 2 units down. All right, so if I want to write this in the format of, say, f of x was 4 to the x, that's a base graph, then what would I do then? Like if I want an f of x minus 2, that would be 4 to the x minus 2, and then if I wanted f of x minus 2 minus 2, then that would be 4 to the x minus 2 minus 2. So f of x minus 2, when I substitute that in, would be the shift 2 to the right, and then that graph would be shifted 2 down from there. So if I'm looking at the notation, it would be this, then this, and then this. But it really, a lot of times we just say y equals, all right? So just try to keep that in mind as we sketch these. But the reason why I point this out is because the base graph always has a point at 0, 1, and 1b, or 1, or in this case. So I'll graph this, a point at 0, 1, and 1, 4, and this should be increasing. So 0, 1, and 1, 4. And then what happens after that is I will go ahead and, oh boy, yes, all right. So I'll go ahead and I'll shift this 2 to the right. All right, so if I shift 2 to the right, then the 0, 1 goes 2 to the right, so it becomes 2, 1. So 2, 1. And the 1, 4 goes 2 units to the right, so it becomes 3, 4. 3, 4. And so now the graph looks like this. All right, so there's a point at 2, 1, and at 3, 4. And then if I shift again, and here, let me get a different color for this. All right, so if I shift 2 down, then I go 1, 2 down, 1, 2 down. So this will be, now the 2, 1 will become 2, negative 1, and the 3, 4 will become 3, 2. And now here's the thing, is that I want you to be clear on the fact that the asymptote was at y equals 0. So here the asymptote didn't move, but here the asymptote needs to be shifted down also. So the asymptote is actually down here now. All right, so make sure that you shift the asymptote down also. And then I graphed this, and this is what I have. There is a point at 2, -1, and at 3, 2. So then I can go ahead and write out what the domain and the range and everything like that is for this final graph here. So the domain is still all real numbers, -infinity to infinity. The range now starts at -2 instead of 0, so -2 to infinity, and the asymptote got shifted down, so it's now y is equal to -2. All right, so if you have any questions about that, please feel free to ask, but I don't think it's too bad. I think that it's just maybe a little bit tedious to see, that. All right, so let's try another one then. This one is a little bit different, or just maybe different in the way you would look at it, because I would rewrite this probably as the, how would I'd probably rewrite that as -2 to the -x plus 3, so that I could see the shift up 3, but I haven't dealt with the negative exponents at all. So what I'm actually going to do then is I'm going to write that as -2 to the -1 to the x power, so that I can rewrite the 2 to the -1 as 1 over 2, like that. So now I have -1/2 to the x power plus 3, and I see that this negative here would be an x-axis reflection, and then I have an x, uh, well, actually, yeah, so I have a 1/2 to the x, so a 1/2 to the x, that is a function with a point at 0, 1, and at 1/2, and it is actually decreasing because the half is between 0 and 1, and then the 3, this is a shift 3 units up. All right, so now I just deal with these things one at a time. So if I deal with them one at a time, here we go. So here's my first sketch. I just have f of x is, let's see, 1/2 to the x. So I point at 0, 1, and at 1/2, and it's decreasing. So it looks like this. So 0, 1, 1/2. And now what I need to do is I will have an x-axis reflection. So that will be negative f of x would be -1/2 to the x. So that means that the y values get multiplied by -1. So I have 0, -1 now, and 1, -1/2, and I see that the graph will look like this now. All right, so this is, what is that? That's 0, -1, and 1, -1/2. And then finally, I have to shift this up 3 units. So negative f of x plus 3, that is the negative 1/2 to the x plus 3. So if I shift this whole graph up 3 units, remember that I am needing to shift the asymptote up 3 units as well. So let me get that that for you so that you can see the asymptote. So here the asymptote did not shift. Here the asymptote did not shift. But here the asymptote will shift 3 units up. All right, so don't forget to shift the asymptote up or down. And then if I shift the 0, -1 up 3 units, 1, 2, 3, it becomes 0 and 2. And if I shift the 1, -1/2 up 3 units, it becomes 1, 2.5. All right, so 1 and 2.5, and so the graph looks like this. All right, so this is 0 and 2 and 1, 2.5 or 2.5, and then you can just write down what the domain, the range, and the asymptotes are going to be. So the domain of this one is still all real numbers, negative infinity to infinity. The range is going to be, well, negative infinity up to 3 now, and the asymptote is going to be y equals 3. So this is all like what we've been doing, the transformations, but just of a different type of graph. All right, so if you have any questions, please, again, feel free to ask, but we're going to do one more. Compound interest. So the one thing that I really need you to look at in this formula is just to break out this formula a little bit so that you can see that you could also write it as p times 1 plus r over n to the n, but then this part is really to the t power. So you can pull out this part in the middle separately if you would like. And that's sort of what I did when I actually I actually rewrote this problem. See how I made the negative x a negative 1 times x? All right, sometimes you want to have the part of 1 plus r over n to the n, and then the t exponent on the outside of that. All right, just break up the two factors in the exponent sometimes because it might make some problems easier to dissect or easier to look at. So a of t is the amount after t years. So that would be generally, in other words, our final amount. And then the principal is usually just, that's what your original amount that you started with is going to be. And then the interest rate per year, a rate means to write it as a decimal and not a percent. And then the number of times interest is compounded per year is n, and then t is the number of years. So for this n, the one thing that I will point out, for example, is if somebody said quarterly, then n would be 4. If somebody said annually, then n would be 1. If somebody said weekly, then they're going to use n as 52. If n is daily, then that would be 365, or say monthly, then 12. So those are some examples of what n could be. So that when I say number of times interest is compounded per year, that's what I mean. And then t is number of years. Make sure that's years, all right, and not like months or like every 2 years or other things that they might trick you with in normal types of problems. All right, so find the amount that results from investing $300. So this is what we want to do. We want to find the amount that result from investing $300 at 7.5% for 4 years and then compound it quarterly. So what we need to do is figure out what information we're told and what information that we need to find. All right, so A of T, P, R, N, T. All right, so I know that we originally invested $300. So that would be the $300. This was the original investment. And then I know that R was 7.5%, or as a decimal, this is going to be 0.075. N was, well, they told us 4 years next, so 4 years is T. N they told us was quarterly, so that would be 4. And then A of T is the amount that we need to find. So this is the amount to find. All right. So now what this means is that we'll have A of T is P 1 plus R over N to the NT. And then I'll substitute in the numbers. So P was 300 and R was 0.075 and N was 4 and T was 4. Now, the good news in a way is that if we were having the final exam in person still, then this is how you would leave the answer, because since there were no calculators allowed on it, you would just leave the answer like this, and this would be one of the answer choices. All right, but in a way, like, this doesn't really mean as much, and so I'm going to use a calculator to give me an approximation. Now, I haven't announced anything about the final exam yet, except that it will be like I'm actually thinking about this, and maybe Courtney and Susan, you can tell me in the chat or whatever you think is easier for you, what you think of this. But I really think that I am planning to give the like either an online final exam, which would be you'll have like a week to study for it at the end, and then take it, or like a small project, but the if you did the project, you could get up to like 20 extra points on it. So the final would be only 200 points, but if you did the project instead, you could get 220 points. That's why I was thinking is that I would give people a choice, because some people don't really do well on taking a like a some people don't do really well on taking a final. Like it just feels like it's a little bit of a issue for like people to sit down, and if you miss one little negative sign, then I can't really give any partial credit. So that's why I thought that I would give an option, but I haven't decided yet. But if people think that's a good idea, then I will probably do that. But it would still be you would have a week to do either the project or the or the final. But anyway, all right. So now I'll go ahead and I'll multiply this together using the calculator. Hopefully you can see this. It seems like it's a little bit I don't know if it's out of focus or something like that, but anyway, 300 times, and that will be 1 plus 0.075 divided by 4 to the 16th power, and that will be 403.8342994. So then if I put this in dollars and cents, then this will be $403.83. All right. So now let's see here. That's it. All right. That's what you have here. And then you would see that after 4 years, the person making, like if you look at this, right, how much did the person actually make in the 4 years? So 403.83 minus 300, right? The person made $103.83. So that was out of the $300 times 100%. So the person actually made 34.61% of their money, and so that was actually a good investment. So that's what compounding means, is that they're making interest on the interest. So even though it was only 7.5% interest, the person overall, after those 4 years of compounding quarterly, made 34.61% interest. All right, so that's actually pretty impressive. All right, let's try another one here. Find the annual percentage yield for an investment that earns 5.5% interest per year, compounded quarterly. All right, so this one actually is, whoops, I'm going to actually write one more thing down, because this is actually in, um, this is actually a uh, very interesting formula, by the way, because the the annual percentage yield is actually the um oh yeah, so the annual percentage yield is actually equal to the final amount minus the initial amount. All right, but the one thing that you need to remember, that annual means that this is the yield after 1 year. So this means the yield after t equals 1 year. All right. So what are we going to do now? Let's go ahead and do this calculation. So we have a of t is p 1 plus r over n to the nt, and they told us that we have, oh, by the way, they told us that we have 5.5% interest per year, compounded quarterly. So they didn't tell us what A is, and they didn't tell us what P is, right? But they did tell us all of the other values. So this is P, and then 1 plus R. So R was 5.5%, or 0.055. So 0.055 over N. N was quarterly, so that would be 4. Quarterly means 4. So over 4. And then T was 1 year. So 4 times 1. And then if I calculate this part here, 1 plus 0.055 over 4 to the 4th power, that is 1.056144809. And so then I know that the final amount was P times 1.056144809, but the initial amount was P. So then I do 1.056144809 P minus P. That is just 0.056144809 P. And so then I see that this is the annual percentage yield right here. So 0.056144809 times 100% would be about 5.6% annual percentage yield. So you see that because you are making interest on the interest, that the annual percentage yield is actually a little bit more than the actual percent that you would get every quarter added on. All right, so that's how the last example it got up to $403.83 so quickly after just 4 years. So that is it on the compound interest and on the exponential function. So let me go ahead and stop this video here.